This was the last week of the 2024 fall semester. Next week is finals week. I'm not going to be here during finals week because I have a conference that I'm going to. The conference, I think I mentioned it in the last video, but I didn't really explain it in too great a detail. I'm really looking forward to this conference, probably more than the other conferences I've been to, and you'll see why in the next video, which will be, during the actual trip. But one of the reasons I like it so much is because this will be the first time I will present a poster of some research that I did with a guy at my previous institution. So it's not new research, unfortunately, that I did with my current advisor. But about 4 years ago during the pandemic, me and my advisor co-wrote a paper that was an extension of my thesis. And we wrote that paper and then we published it in a journal. And it has since got 2 citations, which is exciting. One of the citations, however, improved our results. So my results my result is kind of outdated at this point. But still, I was able to make a poster. It's not in the field of convex geometry. It's more fractal geometry, but it still uses analytical tools to solve the problem that we were working on. And one of the event organizers who I know personally said that as long as it's like an analysis, it should be okay. So I submitted my poster proposal and they said, yeah, you can present. So I'm going to go to the conference. We're going to put my poster up. I'm going to stand in front of it and have people walk by and ask me questions. And it's probably going to go okay. I can't imagine they're going to ask me too deep of questions. But I'm much more mathematically robust now than I was 4 years ago. So I'm pretty confident that I can answer most, if not all, questions they will ask me, unless there's like a genius there that can just see like 13 steps ahead of, what my research is about. So that's why I'm looking forward to the conference next week. I have substitutes coming in to fill in for me during finals week because, I have a class and I have to give a final, but I'm not going to be there. So I have a guy that's going to come in, check attendance, do all that bookkeeping stuff, and answer questions if they arise. I tried really hard this week to make sure that nothing will go wrong, but as you know, no matter how hard you try, something's going to go wrong. So if that happens, they can just call me, and then I'll fix it over the phone, and it'll be fine. What else do I need to say? This whole week, by the way, has been this whole semester was really busy and just teaching and assisting and grading and taking 2 classes and doing presentations. And I know I'm complaining. And then on top of that, you got the research, trying to do the candidacy exam in October, and then it became November, and then it became December, and now currently it's January when we're going to do it. It was just a busy semester, busiest one so far. But this last week was probably the absolute busiest of the 16 weeks we've had. We had a potluck a few days ago. I brought in food and we mingled with everyone. I'm a pretty good mingler, so it wasn't that bad. So I enjoyed the potluck, got to see familiar faces I don't get to talk to too much. We also had a math day event for incoming high school students. So these were all high school students that were thinking about going to our university, and they came in, and I guess they're STEM-oriented kids. So they came in, and we had games for them. They were math-related games. We bought pizza because everyone likes pizza. And most of the volunteers that day were either graduate students, non-tenure track faculty, or actual full-bore professors. And I volunteered for that because they needed some volunteers, and I like helping my friends out. So I manned one of the stations where we played this game of set. I don't know if you're familiar with the set game. I can't remember what it's called. I think it's just called set. But I had never played it before, so I had to learn the rules, and I'm not very good at it, as it turns out. There was one guy there, a high school kid. He came in, he was getting all all of the sets immediately. Like as soon as we laid down 12 cards, he's like, boom, boom, boom. And then he picked them up, took in his body, we replaced them. And then like 2 seconds later, boom, boom, boom. He found another 3 sets. He was interesting to watch, to say the least. But the math day event was a success. We had a lot of fun. The chair of the math department gave a presentation to pitch a bachelor's degree in mathematics to these high school students, and I wasn't there for very long, but I did my part, so I enjoyed my time there. But that's just kind of the tip of the iceberg of what I've been doing this week. For the rest of this video, I guess what I'll do is I'll talk about the 2 homework problems that I plan to write up for my topology final. I don't know what theorem. I'm going to memorize not all of them, maybe like 6 out of the 8 theorems, and just hope that one of the theorems that I studied shows up. My notes kind of fell apart there for a second, so I don't have everything, but I have most of the things. But for this, I'm just going to present the 2 homework problems. The first one is problem number 4, and it's worth 4 points. I need 11, but I did 4 and 6, and which is only worth 10, and I need 11, so that's why I'm doing the theorem. But problem number 4 is pretty easy, actually. It's only worth 4 points, and I'm going to go through the solution here. You have this given topological space X, and you have a subspace Y, and we're given 2 closed subsets of Y. And when I write closed, I mean they're closed in Y. They're not closed in X. They're closed in the subspace Y, such that the intersection of the 2 closed sets is empty, aka they're disjoint. You have 2 disjoint closed subsets of Y. The question is, does it follow necessarily that there exist 2 closed subsets of X such that the 2 closed subsets are disjoint? And if you intersect them with Y, or you can think of it as restricting it to Y, look at the part of F tilde that's in Y, then it coincides with F for I equal to 1 and 2. So basically it's like you have this big space and you look at this space inside and you look at a closed set. I want to be able to extend it in some way to the ambient space that coincides, so that bigger set will coincide with the smaller set when you intersect it with that subspace. That's what property 2 says. And the answer to this question is no, not necessarily. And the example is pretty trivial. You set X equal to the real number line with the usual Euclidean topology that we're all familiar with. You set the subspace equal to R, get rid of 0, or any point really. It doesn't matter if it's 0, it's just 0's a natural choice here. And you set F1 to be the interval from -infinity to 0, the open interval. And you set F2 to be the open interval from 0 to infinity. So F1 is all negatives and F2 is all positives. And my claim is that these F sets are closed in the space Y, and I did it using a sequential argument. You show that any limit point of F1 must be in F1. So take a sequence in F1 that converges to X. If the limit point is in X, or excuse me, if the limit point X is in F2, then you know that X must be positive because F2 is positive numbers. But the sequence is all negative, so it can't converge to that number. Eventually, you'll have to cross 0 and become positive, and that doesn't make sense. So in this case, you know, if X is positive and XK is negative, then the sequence cannot converge to X, which means that your limit point cannot be in F2, which means it has to be in F1. And the argument for why F2 is a closed set is similar. It's the same line of argument. So instead of writing the word same here, I really should write similar. The argument for F2 is similar. So it's not too hard to see why F1 and F2 are closed sets. In fact, we're so deep into topology right now, you probably don't even really need to write this. It's kind of obvious to just state it, but I wrote it up anyway. And clearly F1 and F2 are disjoint. I mean, one's all positives and one's all negatives. So I'm checking to make sure that this first line, or not the first line, but the second line, the middle line where my thumb is verified. So now we need to show that there does not exist sets F1 tilde and F2 tilde. And you can pretty much see that immediately. If you look at the closures of F1 and F2, which is by definition the smallest closed sets in X that contain F1 and F2 respectively, you're going to get these intervals that I've written here. And these intervals overlap at 0. And any other closed set is going to contain the closure, which means that you can only pick up more points. So the best you can hope to do is have a set that contains 0 in the intersection of those two closed sets in X. So we can't make them disjoint. And that's pretty much just the argument. I didn't even write this up when I explained it to him. I just wrote this down. I'm like, yeah, you believe me? He goes, yeah, I believe you. He did say that this problem was kind of not a pity problem, but like he wanted us to be able to do something. I guess a confidence builder. That's the phrase I'm looking for. It was a confidence builder problem. But the real problem that I'm most proud of. Hold on, I gotta make sure that this is actually a good thing to show you guys. I should have checked first. Yeah, this is good. This is problem number 6. It's worth 6 points. And this problem I solved over the Thanksgiving break. I started it, didn't really know, in the beginning you don't really know what to do sometimes. And then I, was with my family over Thanksgiving, and I sat down and was talking to my dad, who was a middle school, high school science teacher. I can bounce some ideas off of him to maybe help, get the creative juices flowing, so to speak. And in the process of talking to him, I realized, maybe I can do this. And then once I saw that, it was just a matter of writing it up and making sure that the whole thing was bulletproof before I presented it to the instructor. But I was quite proud of this because this argument was 110% me. I did not look up anything on the internet. I solved it by myself. I showed it to the instructor, and he said, yep, that's how you do it. So I'm quite proud of myself for this, even if, well, whatever. Let's just read the problem. We want to show that there does not exist a function f from the set 0, 1 cross Sn minus 1, where Sn minus 1 is the n-dimensional unit sphere. So it's not the ball, but it's the sphere of radius 1 centered at 0. Think of it as the boundary of a ball. So that's the domain, and the range, or the codomain of f, is Sn minus 1 again. Show that there does not exist a function f that is continuous, such that two things happen. The first thing is that f0 dot is the identity map on Sn minus 1, which just means that for input 0 here, so this number comes from here, and this is a vector from the unit sphere. Whatever vector you put here, you put the vector here, and then it outputs that same vector. So that's what the identity map is. And then the second property is that f1 dot, meaning that now we are plugging in 1 in any vector from here, is identically constant. And by constant, I mean all of these vectors will map to a singular vector on this unit sphere here. So they all get scrunched up to a point, if you want to speak about it loosely. So we want to prove that no such function exists. And one thing that I first thought of when I was reading this is, okay, so whenever we want to show something doesn't exist, what do? We proceed by contradiction. Assume that it does exist, and then do something weird with it, and show that, that can't happen, so we have our contradiction. So I knew how to start. At least I had that. Proceed by contradiction, suppose such f exists. To make my life a little bit easier, this constant that f1 dot goes to, I decided to give it a name. In convex geometry, a lot of the times for elements on the unit sphere, we use the Greek letter xi. It's the one Greek letter I can't write, but since convention dictates that we use it, I wrote it there. And then for any other unit vector in the n-dimensional space, I call it E. So E is a vector on Sn minus 1, so I can write it as an intuple. So each of these guys are real numbers such that the sum of their squares is equal to 1. And then comes the first trick. We have to define a new function. So we define a function g from this set. Notice how it's the same domain as f, except I'm excluding 1. I'm using the half open interval. And I'm taking this domain and I'm mapping it to the closed ball of radius 1 centered at the origin, which I denote Bn, but I'm going to puncture it at the origin, so I'm removing 0. And the way I define this function is written here. G of Te, where T comes from this interval, E comes from Sn minus 1, is equal to this n-tuple, where we have 1 minus Te1, 1 minus Te2, and then so on and so forth, up to 1 minus Ten. And I did not show this, but I explained it to the instructor pretty well, that G has to be a homeomorphism. A homeomorphism is a continuous bijection such that the inverse of G is also continuous. And if it's not clear what G does from this definition, the picture explains it very well. The domain of G is a can. So you can think of 0, 1, that's where my T comes from. And then at each point along this interval from 0 to 1, you have this n-dimensional unit sphere, which in the two-dimensional case, so if n is equal to 2, you have s to the, this is going to be 1, so you have s1. S1 becomes a circle. It's the unit circle. So to help visualize it, we have the unit circle here at t equals 0. And then as t increases from 0 to 1, we just have a bunch of circles stacked up on top of each other. Okay. You have this can. So you have this can. And since we removed t equal 1, we don't have the top ring of the can. But it's okay. I just wanted to draw a picture of what the domain of G looks like. So what the domain of G does, what G does to the can, is that it shrinks each of these circles into a smaller circle. And it decreases, you can see what happens. When t goes from 0 to 1, 1 minus t goes from 1 to 0. And what it effectively does is it makes these circles smaller when you reach the apex, and you become a cone. So it turns this can into a cone, but you're missing the apex. And then the next part is that it projects it onto the hyperspace that contains the unit circle that's at the bottom. So think of it this way. Takes a can, turns it into a cone, and then once you have the cone, you squish it down until you get a disk at the bottom, minus the origin. So that is what my function G does. So G is a homeomorphism, which means that it is an open mapping, and open mappings take open sets and maps them to other open sets. So that's an important detail that we need later. Second page. Struggling grad student now with more trains. We want to define a new function h from Bn to Sn minus 1, and we do it in the following way. So I define it as a piecewise function. You have f circle G inverse, so it's the composition of G inverse with f of x if x is not equal to 0, and we have h of x mapped to xi if x is equal to 0. I did not draw the really cool picture because that's on a different write-up, but basically what it does is it takes a point on this disk and it puts it on the can, and then it takes it from the can to the unit circle, in the two-dimensional case. And I showed two claims. The first claim is that my function h, so my contradiction is coming from this function h. My first claim is that if you restrict h to the boundary of the ball, then it becomes the identity map, Sn minus 1. And the way I do it is quite natural. You take x on the boundary. It's an n-tuple, so I can write it as an ordered pair of n terms. And because it's on the boundary, you use this definition of h. You use this guy that's up here. So I take h and I replace it with f circle G inverse, which means this. G inverse of x means I map it to the the can. But for this, the t value is equal to 0 because it's on the boundary of the disk. So if t is 0, that means I plug in 0 here, I have x here. But then f is equal to the identity map. F circle dot is the identity map. So I invoke number 1. And if I do that, I get x as my output. So h of x is equal to x if x is on the boundary, and since x was an arbitrary point, we have the result and the claim is proven. Pretty short, pretty sweet, pretty awesome. The next claim is to show that h is continuous on the unit ball, the n-dimensional unit ball. And if x is not 0, it's pretty easy because what we've done is defined h as a composition of continuous functions. But I'd use the sequential argument. So you take x that's not 0 in the unit ball, take any sequence converging to x in the ball, and without loss of generality, we can assume all terms are non-zero because if you think about it, it has to be, if you put any disk around x, no matter how small it is, the sequence has to be trapped inside that disk for a sufficiently large index. So you just make it small enough so that it doesn't contain 0, and then all the terms have to be non-zero. You can write it that way, or it doesn't matter. You're just interested in what happens when k is near infinity. And xk can't be 0 when k is near infinity. So you pass it through the limit, you take the limit of hxk. So I have to edit these two parts together because I ran out of storage. First time I've edited a video on this channel, but I think I left off at this part where I showed that the limit of hxk as xk tends to x is equal to h of x. And this is pretty easy to see. All you have to do is invoke the definition of h. We can do this because xk is not 0. And because f and g inverse are continuous functions, you know that this limit is equal to f circle g inverse of x, which is h of x. And since x was an arbitrary point, an arbitrary non-zero point, we know that h is continuous on bn minus 0. So that proves the continuity outside of 0. So what happens at 0? You have to be a little bit more delicate with this, but really it's just invoking the definition of continuity a couple times, plus some other things. But the way we do it is you take an open neighborhood of xi, which remembers that that constant that we had at the very beginning that f1 of e maps to, so that's the second line. For any vector e, f1 of e is equal to xi. Because we assumed that f was continuous, we know that there exists a neighborhood for us, waiting for us, ve of 1.e, this guy, in this can, such that f of ve is a subset of u. And then we collect all of those ve's. We put them together into one magnificent set called v. Here it is next to my thumb. That's an open neighborhood in the can. And if we pass it through the function, look at the image of v. We take f of v, that's f of the union, and we can pull the union out. So we have union f of ve, and those f of ve's are all subsets of u, so the full union is also a subset of u. So that's good. Now, I don't know if I really need this fact here, but I kind of gave it a name in case I needed to use it to explain something. But I define f prime to be f minus the top circle of my can. So here I'm fixing t to be 1, and I'm looking at the top circle of the can. And it's an open set because that top circle is a compact set. In fact, I called it R because it looks like a ring, like an actual physical ring, not like a ring from ring theory. Just it looks like a ring, so I called it R. And I noticed that the complement of V in the can is also a compact set. Moreover, the complement of V and that top ring are disjoint. Their intersection is empty. So the distance between those two disjoint compact sets are positive. And because it's positive, I can choose an epsilon such that epsilon is less than the distance between those two. Specifically, I want it to be like half or a third, it doesn't matter, of the minimum distance xy, where x is from the ring and y is from the complement. In fact, I drew a picture here. So The idea is that I can choose an epsilon small enough to where I can define a band of circles, which I defined E, I've shaded it here, that forms an open neighborhood of the top ring, such that E is completely contained within V prime. That's what I really want to say. And I've explicitly defined what E is here. So it's all these vectors, where E is an arbitrary vector from the circle, and T is somewhere between 1 minus epsilon and 1. So as a picture, this is what we have. And if I pass E through my homeomorphism G, I'll get the punctured ball of radius epsilon centered at 0. And it's an open set, which is nice. And lastly, if I throw the circle, or not the circle, but the origin inside of GE, then I'll get the epsilon ball, subset of Bn. And if I pass it through H, then H of the epsilon ball is definitely going to be a subset of U. And I could explain this step a little bit more in detail, but it should be obvious, at least from the picture, because look what happens. You take H of E, which is F circle G inverse. G will cancel with G inverse here. So now you have F of E. F of E is a subset of F of V, and F of V is a subset of U. And by definition of continuity, you have continuity at 0. And since you have continuity at 0, you have continuity now in the whole disk. Now, you're asking yourself a question. I know it. I can hear you asking the question through the screen. Why did we do all this? Where's the contradiction? Come on, you have this function h. What's so special about it? And the answer is that you can now invoke Brouwer's fixed point theorem, which is a huge monstrous theorem from class, which says that if you have a function, big F, defined on the closed unit ball that maps to its boundary Sn minus 1, such that F fixes the boundary, which is whatever in here, then Brouwer says that no such function F can exist, or no such F can be continuous. But the function we just defined, the H function, maps the ball to its boundary, is continuous, and fixes the boundary. And Brouwer says that that cannot happen. And that's where the contradiction comes from. Overall, this problem took 4 pages, but really, I think we can get it down to fewer pages. But with my teacher, I take no chances. I wanted a bulletproof argument, and he's going to get a bulletproof argument. So I think this video, after editing this one with the last one, will make it go on a little bit longer than I want. But it was totally worth it, and I really need to grade my students' last quiz because I have a lot of grading to do over the next few days, and it's not going to be fun. Plus, I'm doing the candidacy in January, and that's just going to be there's not going to be any resting over Christmas. It is going to be not fun for the struggling grad student. But I am optimistic, so don't worry about me. All right, goodbye.